Hi students. In the previous session, I had given you an introduction to the grand canonical ensemble and the grand canonical distribution function. In a grand canonical ensemble, we considered open systems which can exchange energy and matter between the surroundings, between the system and the surroundings. Allowing the exchange of matter makes capital N, the number of particles, a variable in addition to energy. Here both the number of particles and the energy are variables. So in a grand canonical ensemble, we have a large number of systems. That means these are the mental copies in the ensemble. We have a large number of systems which are defined by, or whose macro states are defined by, a constant volume, a constant temperature and constant chemical potential. That is, these systems can exchange energy with the reservoir, but their temperatures must be maintained a constant. They can exchange particles with the reservoir too, or they can exchange particles also, but their chemical potential must be maintained a constant. So, the macro state of the Mendel copies in a grand canonical ensemble, or the macro states of the systems in a grand canonical ensemble, is defined by a constant volume, constant chemical potential and constant temperature. And we also discussed about the grand canonical distribution function, that is how these systems are distributed. So, as per the distribution function, we found out that the probability that a system has energy Es and number of particles Nr is given by PRS is equal to e raised to minus beta Es minus alpha Nr divided by sigma Rs e raised to minus beta Es minus alpha Nr. This gives the probability that a system has energy Es and number of particles Nr. That is the grand canonical probability distribution function. Next, what we have to discuss is how, using the grand canonical ensemble formulation, we can find out the thermodynamics of any given system. For example, we know as per microcanonical ensemble formulation, what did we do? We found out the number of accessible microstates for us associated with a system. That is, we determined omega. From omega, we determine the entropy S equal to K ln omega of the system. From S, we found out all the other thermodynamic quantities related to the system. So, that was how we found out the thermodynamics of a system using microcanonical ensemble. In canonical ensemble, what did we do? We determined the partition function associated, and from the partition function, that is Q, we determined Q V of t is equal to sigma e raised to minus beta Es. So, we found out the canonical partition function, and using this partition function, we determined the Helmholtz free energy A is equal to minus KT ln Q. From that, we determined all the other, say the internal energy, entropy, Cp, Cv, all the other thermodynamic properties of a given system. Similarly, how do you connect grand canonical ensemble formulation and the thermodynamics of a system? That is what we have to learn next. But before going to that, we must have a bit more information or a bit more knowledge at hand. So, we are going to consider an ensemble of capital N identical systems. That is, there are capital N Mendel copies of our system in our ensemble, which are mutually sharing, or which are sharing among themselves an amount of energy N into E bar. That is, the total energy that they share among themselves is given by N into E bar. N gives the total number of systems into E bar, the average energy. That is, we are getting the total energy shared among all the systems, and they are also mutually sharing n into n bar number of particles. That is, my ensemble consists of a number of systems which are mutually sharing n E bar amount of energy and n bar amount number of particles. That is, total number of particles are given by the total number of systems into the average number of particles. That is n into n bar. Okay, so that is our state. Now let us consider small n subscript rs. nrs represent the number of systems with energy Es and having nr number of particles. So nrs, small nrs represents the number of systems among these total capital N systems. How many systems are having energy Es and number of particles nr is given by nrs. Suppose I am saying n11, 11 equal to 10. That means there are 10 systems having n1 number of particles and having E1 amount of energy. Suppose I say n12, that means equal to 5, means there are 5 systems having n1 number of particles and E2 amount of energy. So these nrs give me the number of systems having a particular number of particles nr and a particular amount of energy Es. Now the members in my ensemble or the states in my ensemble must follow these 3 conditions A, B and C. So let's see what are the conditions. That is, sigma nrs must be equal to n. That is, if you add up all such states, that is the number of states, if you add up, you must get the total number of states in the system. Surely if you add all the possibilities of the number of states, all the number of states with different amounts of combinations of energy and number of particles, different Es and nr, when you add them all together, you will get the total number of states in the ensemble. Next, next condition that must be satisfied by the members in my ensemble or by the states in my ensemble is that sigma nrs Es must be equal to n into E bar. N E bar stands for the total amount of energy. We have seen it here. It stands for the total amount of energy. So that is, number of states into average energy gives me the total energy. Is it equal to sigma nrs into Es? That is what we have to check. Suppose there are 10 states. Now nrs states stands for the number of states. Suppose there are 10 states with energy E1, 5 states with energy E2. Then the total energy is given by 10 E1 plus 5 E2. That will give me n E bar. That is the total energy of the entire system. That is what we have done here. That is the number of state into the energy of those states. If you add them together, you will get the total energy for possible for the ensemble. Next, what we do is, the condition that our ensemble must satisfy, the states in my ensemble must satisfy is sigma nrs into nr is equal to n into n bar. N into n bar, that is total number of states into average number of particles in each states. That is, it gives the total number of particles possible in the ensemble. So is it correct? Yes, we multiply, say there are 10 states having energy. Suppose there are 10 states having energy 10 states having, say, n1 number of particles, 5 states having n2 number of particles, 5 states having n3 number of particles. Then how do I get the total number of particles? I do 10 into n1 plus 5 into n2 plus 5 into n3 gives me the total number of particles. That is, total number of particles is given by n into n bar. So these conditions must be satisfied by the members of my ensemble, the mental copies of the states present in my ensemble. Okay, so we are considering such an ensemble of n identical systems satisfying the following conditions. So we see that here NRS, the set NRS represents the different modes of distribution of particles and energy among the members of the ensemble. Suppose I write, it must be a set. Suppose I write a set of numbers NRS. Each NRS represents what? It represents the different modes of distribution of energy and particles. It's not energy alone, it is the different modes of distribution of energy and particles among the members of the ensemble. And any one such mode can be realized in W different ways. Any one such mode can be, and that we have learned earlier, that is any one mode, a particular mode of distribution of energy and particles can be realized in a number of ways. We have different ways to realize the same combination of energy and same combination of energy and number of particles, and the different ways to realize this is given by W is equal to capital N factorial by NRS, the product of NRS factorial, pi NRS factorial. So that will give you the number of different ways in which a particular mode can be realized. So the set NRS gives you, the set of numbers in the set NRS gives you the different modes in which the energy and particles can be distributed among the different members of the ensemble, and every single mode can be realized, or every single mode can be achieved in a number of different ways given by W is equal to N factorial by sigma RS, not sigma, it is pi RS NRS factorial. That is the product of each of the members in the set. Now, which will be the most probable mode out of all the possible modes? Which will be the most probable mode? Like how we told before, which is the most probable possibility of an energy state? That is the state which is the greatest in number. Similarly, the most probable mode of distribution, that is N star RS, the most probable mode of distribution N star RS is the one which maximizes W, that is which gives the maximum value for W, will be the most probable mode. And we know from the derivations in canonical ensemble, N star RS by capital N will be equal to e raised to minus beta es minus alpha NR divided by sigma RS e raised to minus beta es minus alpha NR. That is our probability distribution function in a grand canonical ensemble. N star RS by N, that is the most ratio of the most probable distribution divided by the total number of systems, is equal to e raised to minus beta es minus alpha NR by sigma RS e raised to minus beta es into N. Minus beta es minus alpha NR. Now we see that in the limit, when n tends to infinity, when n becomes very very large, the average value of NRS by n will be nearly equal to, it is not NRS, it is N star RS by N. The average value or expectation value of NRS by N will be equal to the most probable value of NRS by N, that is equal to, which is equal to e raised to minus alpha NR minus beta es by sigma RS e raised to minus alpha NR minus beta es. That is the probability distribution function. The distribution function PRS will be equal to NRS by, that is the average value of NRS by N. We get PRS is equal to the average value of PRS is equal to the average value of NRS by N. Okay, so I hope this is clear. So if we got PRS is equal to average value of NRS by N, we can write down the average energy as sigma RS ES into it is actually PRS. So in the place of PRS, I am writing average value of NRS by N, and average number of particles N bar should be equal to sigma RS NR into PRS. So in the place of PRS, I am writing average value of NRS by N. Okay. So based on this calculation, I have written the equations for average energy and average number of particles. We know actually average energy is given by E bar is equal to sigma RS ES into e raised to minus beta ES minus alpha NR divided by sigma RS e raised to minus beta ES minus alpha NR. That can be replaced by PRS, which can be replaced by the average value of NRS by N. That is what we did here. Now we are going into the connection between the grand canonical ensemble and thermodynamics. With this information, I am going to that. So what is done in the grand canonical ensemble formulation is we derive or we define the equation for the grand canonical partition function. We define the equation just like in the canonical ensemble formulation where we defined the canonical ensemble canonical partition function. Here we define the grand canonical partition function. Okay, grand canonical partition function QGC, and we can also define something called a quantity called or a parameter called Q potential. So either using the grand canonical partition function QGC or by using the Q potential, we can find out all the thermodynamic properties related to the system. We have to just calculate just as in the case of canonical ensemble formulation where we only calculated the partition function of the system Q NVT, and from that I derived all the thermodynamic quantities related to the system. Similarly, here I have to derive or I have to find out only the grand canonical partition function QGC or the Q or another parameter called Q potential represented by small q, and from either of these two I will get all the thermodynamics related to my problem or related to the system under question. So now let us see what is the grand canonical partition function and what is this Q potential. So we have got PRS equal to e raised to minus beta ES, that is the probability that a system has energy ES and number of particles NR. That is our distribution function as PRS is equal to e raised to minus beta ES minus alpha NR divided by sigma RS e raised to minus beta ES minus alpha NR. Here the grand canonical partition function is given by this term in the denominator, just like how we wrote the canonical ensemble canonical partition function. So QGC is equal to sigma RS e raised to minus beta ES minus alpha NR is the grand canonical partition function. Now the new quantity that we define is called the Q potential is given by small q is equal to natural logarithm of the grand canonical partition function. It is ln QGC. Small q is equal to ln QGC. Now by either knowing any of these, that is either the grand canonical partition function or the Q potential, we can determine all the other thermodynamic quantities related to the system. Okay, here I told you Q is equal to log of QGC, that is equal to log of sigma RS e raised to minus beta ES minus alpha NR. Now I am going to derive exactly what is this Q potential, or I am going to derive another expression in terms of pressure, volume, temperature, etc. for Q potential. What is exactly my Q potential? So what we are going to do here is we are going to begin with Q is equal to natural logarithm of QGC, that is sigma RS e raised to minus beta ES minus alpha NR, and I am going to find out the derivative of Q. dq is equal to, so what I do is I just differentiate this equation. I get it as this. Okay, from this I isolate out E bar d beta and N bar d alpha. As you know, E bar is equal to ES into sigma rs es e raised to minus beta es by alpha nr divided by this term sigma rs e raised to minus beta minus alpha nr. So I got this term as instead of simply writing minus es d beta, I got it as minus e bar d beta when I multiplied it with this term and these two, that fraction. And the next term minus nr d alpha, that too on multiplying with this term and this term I get it as minus n bar d alpha into the remaining terms I am just writing in the same manner. Here we know e raised to minus beta es minus alpha nr divided by sigma rs e raised to minus beta es minus alpha nr is my probability distribution function PRS, which can be replaced by the average value of NRS divided by capital N, which we learned just before. So it can be replaced by average value of NRS by capital N. So that is what we did here. dq is equal to minus n bar d alpha minus e bar d beta minus beta by n into sigma nrs des minus alpha by n sigma rs average value of nrs into dnr. But average value of sigma rs average value of nrs into dnr is equal to 0. So only 3 terms exist in my dq. dq is equal to minus n bar d alpha minus e bar d beta minus beta by n into sigma nrs des. Now what I do is I just maintain this term on one side and take all the other terms to the LHS, so that I get dq plus n bar d alpha plus e bar d beta is equal to minus beta by n sigma nrs into des. Now what I do is I want to write this equation that I have here in this form, that is d of q plus n alpha plus beta e. To get that, what I should do is I have to add alpha dn. This I will get it as d into n alpha only if I have n into d alpha plus alpha into dn. Now I have with me only n into d alpha, so I just add alpha dn plus similarly to get d of e beta. To get d of e beta again I have to have 2 terms. One is e d beta which I have with me and beta de which I have to add. So I added those 2 terms here, but when I add them here I should add it on the other side also. So I gave it to both these sides so that I can write my LHS as d of q plus n alpha plus beta e is equal to, I took beta common factor out from here so that I get beta into minus of sigma rs average value of nrs by n into des plus alpha by beta into dn plus de. Okay, this I give it as equation 1. Now what we are going to do is I am going to compare the RHS of this equation, that is this part inside the parenthesis or inside the bracket. I am going to compare it with the first law of thermodynamics, that is dq is equal to dE plus delta W plus mu dN. How can I simply compare a number of terms with or how can I simply compare these terms or equate it with the first law of thermodynamics, with the equation corresponding to first law of thermodynamics? Can we simply do it like that? We can't do. So there must be some logic behind doing it. So what is the reason for doing that? Now you look at your LHS, this side. Now here we are finding out the derivative of q. Q is equal to log of capital Q Gc. That means it is a dimensionless quantity. My next term is n into alpha. What is alpha? It is alpha is minus mu by kt. N mu is energy and kt is again energy. So energy by energy, it's dimensionless. Next is beta by E. E is energy and beta is 1 by kt. Again another dimensionless quantity. So this side completely consists of some kind of dimensionless quantity. So on the other side also it should satisfy that condition. Now on this side I have beta into something inside the bracket. Beta means 1 by kt, that is 1 by energy, into, that means the terms inside my bracket, that is these terms must have the dimension of energy. Now our first law of thermodynamics gives dq equal to something, that is it has the dimension of energy on both sides. So I am comparing the terms inside the parenthesis with the first law of thermodynamics. So I hope it is clear to you. So what I am going to do is I am going to equate this with this, or I am going to replace these with this, or I am going to replace the whole thing with dq. Okay, so what I am going to do is, I equated the terms inside the bracket with the first law of thermodynamics, so that I can replace this whole thing with dq, or the whole thing inside the bracket with dq. So dq plus n bar alpha plus e bar beta is equal to beta dq. Okay, so next what I am going to do is I am going to replace this beta with 1 by kt. I am going to replace beta with 1 by kt, and dq I am going to replace it with, I know dq is equal to tds. So I am not changing my LHS in any manner, but RHS I am going to write it as 1 by kt into tds, so that I can cancel t and t and I get the answer as 1 by k ds. Or it can be written as d of q plus n alpha plus e bar beta is equal to d of s by k, because k is a constant. So I can cancel off the derivative operation, the differential that I am trying to do on both sides can be cancelled, so that I get the answer as q plus n bar alpha plus beta bar is equal to s by k. Here again I am going to substitute for alpha. In the next step I am going to substitute for alpha and beta, so that I get q is equal to s by k minus n bar mu by kt plus e bar by kt is equal to, which is equal to, I took the LCM, st minus n bar mu plus e bar by kt. That is my q. So when I simplify, I get q is equal to st plus n bar mu minus e bar by kt. But what is n bar mu? It is the Gibbs free energy, which can be replaced by a plus pv or e bar minus ts by p. That I am going to substitute here, e bar minus ts plus pv, so that I get small q is equal to st plus e bar and e bar will cancel, st and t minus ts will cancel, so that I get my q is equal to pv by kt. So this is my q potential of the system. Q potential of the system is equal to pv by kt. So I've got the various equations for the q potential. Q potential is the log of the natural logarithm of the grand canonical function, partition function, or q potential is equal to log ln sigma rs e raised to minus beta es minus alpha nr, and q is equal to pv by kt. So with this we have got the different equations for q. So q is equal to ln sigma rs e raised to minus alpha nr minus beta es. So I am going to substitute in this equation sigma rs e raised to minus beta es is my canonical partition function. So I am going to substitute with that. Sigma s e raised to minus beta e is equal to qnr. So I can write my q potential as log of sigma nr tending from 0 to infinity qnr e raised to minus alpha nr. So we have to number only over the number of particles, that is nr. And I am going to make one more substitution here, that is e raised to minus alpha. I am going to replace it with z. E raised to minus alpha equal to z. And this e raised to minus alpha is called fugacity. It's called the fugacity. So I am going to replace with fugacity, so that my equation becomes e raised to minus alpha nr becomes z raised to nr, or my q potential can be written as q is equal to ln logarithm of sigma nr equal to 0 to infinity qnr, that is the canonical partition function, into z raised to nr. where QNR z raised to nr is my grand canonical partition function. So we have learned the different forms of the Q potential and how is it represented in various ways. Q potential can be represented as log e raised to minus alpha nr minus beta ec. It can be represented as log of the grand canonical partition function. Q is equal to PV by KT, and if you substitute with the canonical partition function and fugacity, you get Q is equal to log of sigma n equal to 0 to infinity QNR z raised to nr, where QNR z raised to nr is the grand canonical partition function. I think we can end our session here, and in the next session we'll go into the details of the connection. How do you connect the grand canonical partition function and the Q potential with the thermodynamics of any system. I hope this session is clear to all of you. If you have any doubts, please do contact. Thank you.